Hello, everyone. This is Andy Fingerhut, co-chair of the P4 Architecture Working Group, and Antonin, our speaker today, is co-chair of the P4 Runtime API Working Group, and has been so, I think, for at least, what, 3 years now, I think, Antonin? Is that right?
Yes, because that's how long the working group has been around. So.
Yes, and you were there from the beginning. Okay, so I'll go ahead and turn it over to you, Antonin, and go right ahead.
All right, thanks. Thanks everyone for joining. So the purpose of the talk is, well, not so much to give an introduction to P4 Runtime, although I can touch on that briefly, but it's more to describe how P4 Runtime is supported currently in p4.org software, and for people interested in contributing, what should they look for, and what kind of tasks need to be tackled, especially in the context of PSA Switch, how to provide P4 runtime support for that BMV2 target. It's not. All right, so hopefully you can still see my screen. So a tiny bit of history before we dive into it. So the first BMV2 commit and the date at which BMV2 was open source was in January 2015. Surprisingly enough, actually BMV1 was open sourced after BMV2 was initially open source, which is quite funny, but I think before that date, March 2015, BMV1 was mostly developed internally at Barefoot. Then at the beginning of 2016, the first major release of BMV2 was published. I think I did that at the time because we basically had reached feature parity with the first version of the behavioral model. And the main differences between the two was that BMV1 was auto-generated C code, which was generated from the P4 program by a compiler and then compiled into a binary by GCC or NEC compiler, whereas BMV2 was kind of like a C++ project that moved away from code auto-generation from the P4 program, and that has advantages, but that also has a few drawbacks, and maybe I'll talk about this later. But moving away from code auto-generation is kind of like important in the context of P4 runtime, where one of the key aspects is that you can push a new P4 program, a new pipeline to the switch and control it without having to restart anything, any process on the switch side. So to be able to test P4 runtime effectively, it's kind of important to have a software model that for which the code doesn't really need to change when you change your P4 program. Later that year, we also started to work on PI. When I say we, that was mostly me at Barefoot Networks at the time, which stands for a protocol independent. And this was meant to be a new API for P4 data planes, which would also not be auto-generated. So until then, we're working with an API called PD, a program dependent, which was auto-generated from the P4 program. And same thing as before, it would require like code changes and binary changes and reloading dynamic libraries when switching from one P4 program to another P4 program. So we started to work on PI, and shortly after that, the P4C compiler introduced support for the BMV2 backend for the very first time. So until then, the code was, the inputs to BMV2, which is a JSON file representing the P4 program, was generated by a Python compiler, which is no longer maintained today. Then in 2017, we introduced a new BMV2 target, Simple Switch GRPC, with support for P4 runtime. At that stage, P4 runtime was kind of like a prototype that was being worked on jointly by Barefoot Networks and by Google, and it kind of like had evolved from the PI project. That year, we also created the P4 API working group. We deprecated the first version of the behavioral model, BMV1, P4C behavioral. That was a busy year. There was also the first demonstration of a physical network running switches controlled by P4 runtime. There was a joint demo in Amsterdam by Google, Barefoot, and ONF. And then more recently in 2018, the PSA Switch target was introduced for BMV2. There was also BMV2 support in Stratum, which was an important milestone. Stratum is a network operating system maintained by ONF, the Open Networking Foundation, which uses P4 Runtime as one of the APIs to have communications between the controller and the switch. And then in 2019, after a long time, actually, I didn't realize it was that long, we released the first version of P4 Runtime. And since then, we've had 2 new releases of P4 Runtime. And another important milestone was last year, we got assigned a port from YANA, port 9559, specifically for P4 Runtime. All right, so I think everyone should be familiar with that picture. It kind of shows the workflow when you work with a P4 program and the part played by the runtime APIs. So I don't think I'm gonna go into the details here, but P4 Runtime is what's in red here. Basically, how do you control the entities defined by your P4 runtime, by your P4 program at runtime using a set of standard APIs? And I'm going to skip this one, but basically, why a new runtime control API specifically for P4, and why a new one even for P4, because we had other APIs before that. So this kind of shows the 2 dimensions you can use to evaluate an API, and how P4 runtime compares to previous APIs. So the first 2 here were like specific to P4, you can see the one I mentioned earlier, auto-generated APIs. So early on in the lifetime of P4, the trend was to have APIs which were auto-generated based on the P4 program. And there were different such APIs for different vendors, but basically the idea was always to kind of like auto-generate C code or C++ code or something else based on your P4 program. So unlike all those other APIs here, P4 Runtime aims to be both target independent, so portable across targets and vendors, and protocol independent, which we can summarize as when my P4 program changes, when I introduce new concepts in my P4 program, the API itself doesn't need to change because there is no code generation and no protocol embedded into the API, unlike in OpenFlow, for example. I'm going to skip through this slide here. I think I've covered all of this before. The idea, once again, is that P4 Runtime is program independent, and you have the ability to push a new P4 program to a network device which supports P4 without recompiling any code. I'm going to assume everyone knows about protocol buffers, protobuf, and GRPC, which are the messaging and RPC mechanisms used by P4 Runtime. Here you can see that kind of like one of the design principles for P4 Runtime was to keep the number of APIs, the number of RPCs pretty small. And so we actually have only 6 different RPCs, which in my opinion, makes the API easier to use and easier to understand and learn. So you have a write RPC to basically write something, for example, insert a new table entry to a P4 table. So read RPC to read contents from the P4 database. That can be table entries, that can be counter values, some external configuration, and so on. Then you have 2 APIs, and this is like kind of like really what the novelty is in P4 Runtime, to configure the pipeline of your networking device, and it's called set forwarding pipeline config. It takes an argument which is basically the output of your P4 compiler. So it's not a P4 program, but it's going to be the output of your P4 compiler, and a part of that message is target independent, and a part of that message is going to be like target specific. In the case of BMV2, the target specific part is just a BMV2 JSON file. In the case of hardware vendors, it can be like some binary blob, for example. Get forwarding pipeline config does the opposite. It allows you to check which was most recent pipeline configuration you've pushed to your program. Then you have an important RPC, I guess they're all important, but which is like a stream channel between a P4 Runtime client and a P4 Runtime server running on the network device. And everything that needs to happen kind of like asynchronously is going to happen on that channel. For example, sending packet messages. So a well-known concept for SDN is packet I/O, right? So your device needs to send a packet from the data path to the controller, and the controller needs to be able to inject packets in the data path. So that's done using that RPC stream channel. And finally, the latest addition, which wasn't in the first release of P4 Runtime, is the capabilities RPC. And really it's kind of like to check, right now it's mostly to check which version of the P4 Runtime interface is implemented by the switch. In the 1.x releases of P4 Runtime, we preserve backwards compatibility, but sometimes you need to be able to know which minor release of the P4 Runtime API is implemented by the network device in order to potentially impact your controller logic. In the future, I think this RPC could be used to different things for different things as well. Maybe, I don't know, check feature support, for example. I think I'm going to skip that, and I think I have an example later. Let's see. Yeah, I'm gonna talk about the P4 Runtime workflow. It's important, and I'll do a demo of that later. But basically, let's assume you have your P416 program test.p4, and you want to run it on simple switch GRPC, and you want to control it using the P4 Runtime API. From a control plane perspective, the fact that it's running on BMV2 and on simple switch GRPC is not really relevant. Your table entry messages, for example, to insert table entries in the data plane would be the same across multiple targets, so long as your P4 program is basically the same. So you're going to run the P4C compiler on your P4 program, generate like a P4 info message, and in the case of BMV2, the JSON file, which is used to configure BMV2 at runtime so that it can implement or emulate your P4 program. So the P4 info part is only depend on the P4 program and is the same for all targets which support P4 runtime. So that's a target independent part of the pipeline configuration that you need to send to the device. And BMV2 JSON here is what I was talking about earlier, which is a target specific part of the pipeline configuration. So you're going to combine those two, and using the set forwarding pipeline config RPC that I talked about previously, you're going to send that pipeline configuration to the P4 Runtime Server, which is part of the simple switch GRPC process, and we'll cover that in more details later. Once this is done, you can send things like table entry, you can read table entries. Basically, you're going to move into the management of the P4 entities defined in your P4 program. That's an example of a P4 info message, if you've never seen one before. So I think it's pretty easy to understand. And I think usually it's fair to say that generation of the P4 info is pretty straightforward in the compiler. So some code that I think most people should be able to understand, contribute to, or modify if needed. But basically, we're going to extract from the P4 program, in this case, all the information for that action and that table, which are relevant to a controller and to runtime operations. I think, so basically this is going to be like interface level operation. How many match fields does my table have? What's the match type for those match fields? What's the type of those match fields? I mean, right now in the case of P4 runtime, we only encode the bit width, so the type is like assumed to be a fixed bit width integer. And then same thing for an action. What are the action parameters for my action? Which tables are referencing this action, and so on. You'll notice that everything which is specific to the action implementation, for example, is not relevant to my controller. We assume that the controller knows what the action is doing, and you just need to be able to refer to that action either using a name or an ID. In here, we have kind of like for that very table, we have an example of a table entry message. So this time it's no longer in the context of P4 info, it's in the context of P4 runtime itself. So if you wanted to add a table entry into that table using P4 runtime, what would the message look like? So basically here, once again, you have the table declaration, kind of like a logical view of the table operation I'm trying to do here. So if I match this prefix, I want to be able to forward packets out of this port and with that destination MAC address. And this is what this table entry encoded using P4 runtime is going to look like. When the P4 runtime server is going to receive that entry, it can validate that it's a correct table entry for the table using the information included in the P4 info message, which I was showing you previously. So as an example, here, my table entry includes one match field value. It's a value for LPM match field, and I can validate that based on the information included in the P4 info here. You can see that for that match field, the match type is indeed LPM. And once again, the bit width information can be used to validate the values provided by the controller. Won't go into details here because I've been talking about set pipeline config a bunch already, but yeah, you can see that the key part of this is this message, which combines the P4 info message, which is target independent and is needed by the device, for example, to validate P4 runtime messages like table entries. And then you have a binary blob, which represents the target specific part of the P4 configuration. And in the case of the BMB2 JSON, this is just the JSON string as generated by the compiler. Let me skip over packet IO. Those are not super important either in the context of this talk. So I'm going to switch directly to talking about the implementation. But does anyone have any questions so far? All right.
Will the slides be available somewhere, Antonin?
Sorry, say that again, please.
Will the slides be available after this?
Oh yeah,
I missed that first brief history slide, so I was curious.
Yeah, no worries. I think Andy already has them. I haven't changed them since sharing the slides with him yesterday, so I think he can post them after the talk.
Awesome. Thank you.
All right, so post your question in the chat if you have another one. So these are the main P4 runtime server implementations today. Actually, this slide is borrowed from Max at ONF. It's not one of my slides. The implementation on the right, I guess, is not completely a secret because otherwise it would not have included it in the slide, but I don't believe this code is open source yet. So today we're going to focus on let's call it the P4 Lang, P4 Runtime Server implementation, which is also referred to as PI. Which is maintained by me. So it doesn't claim to be a better implementation than the others or a more conformant implementation than the other. I think there is kind of like a parity between the PI1 and the Stratum implementation at least, but it's hosted by p4.org. So here is kind of like the life of a P4 runtime message in the context of p4.org software when using simple switch GRPC. And I think at this point, it's fair to say that the talk is going to get quite technical and steered towards people who are likely to play with this implementation or to extend this implementation. So let's see how it goes. So you start at a P4 runtime client, for example, your SDN controller, like the ONOS controller from ONF. And you're gonna generate your P4 runtime protobuf messages and send them to a P4 runtime server using the P4 runtime RPC, such as write. Now, the P4 runtime server code is hosted in the PI repository. Yes, on P4 Lang, sorry. And that part of the code, and I really like separated all the different layers here. is very simple. What it does is it's going to enforce what we call in P4 Runtime leadership arbitration. So in P4 Runtime, you can have like multiple clients connected to a P4 Runtime server, and they can be quote unquote competing for control of a specific network device. So while P4 Runtime is not in charge of electing a leader among those clients, which is going to be responsible for programming the network device, it's in charge of doing arbitration, which means that the P4 Runtime server should only accept messages from the client with the largest election ID. So each client would receive an election ID from your consensus layer, and then advertise that election ID to the P4 Runtime server, and the P4 Runtime server would kind of like arbitrate between those, and it would look at the one with the highest election ID and tell, okay, you're the leader, you can send me right RPCs, you can configure the pipeline. And to any other client, it would say, okay, you're not the leader, there is someone with a higher election ID. And so I'm basically gonna ignore everything you send me and return an error to you. So that server layer here, which is hosted at, under this directory, is just responsible for arbitration enforcement. And once it validates the messages and updates the arbitration state, it's going to forward the P4 Runtime protobuf messages to some API, which is called Device Manager, and which is also hosted in the PI repository. So between those two boxes here, client and runtime server, this is like an RPC, GRPC messaging layer. But between those two layers here, it's going to be just like a C++ API call. However, we kind of like preserve the protobuf message, so we do not do any transformation at this stage. And I'm going to quickly show what this interface looks like. It's also a very simple interface, and you can see that for each P4 Runtime RPC, such as write, we have a corresponding API call, and that the parameter for that API call is just going to be the P4 Runtime protobuf message. So really, there is no transformation up until that stage. This is kind of like supposed to be a semi-standard API, which enables us to decouple the server implementation itself from the P4 Runtime message implementation or enforcement.
Antonin?
Yep.
In this picture, everything from the P4 Runtime server box on down, in the Simple Switch gRPC case, it's all in the same Linux process. Let's say if you're running a Simple Switch gRPC on a Linux process. Is that true? That's
correct. Yeah. And one consequence of that, I think I touch on that later as well, but is that you can only have one, in the case of BMV2, you can only have one switch or device per P4 Runtime server. So basically, even though you do have to provide the correct device ID when you send your P4 Runtime messages to the server, there can only be one valid device ID because there is only one instance of a BMV2 switch as part of that process. If that makes sense, yeah. So once we've called that device manager, basically we're gonna, I mean, there is a lot of logic here, but we're gonna switch from C++ to C. And I think that layer is mostly there for historical reasons. If you looked at the history I shared at the beginning, it all started with like the PI library, and then we started collaborating with Google, and we decided, oh, it would be good to standardize around like a protobuf and gRPC interface. And all of this, which is P4 Runtime, was built on top of the PIC library when it comes to implementation. So the device manager implementation is going to be in charge of transforming the P4 Runtime messages into standard C API calls. So at that point, the representation of everything is going to change. We go from a protobuf message for a table entry to basically a list of structs for the match part of the table entry and the action part of the table entry, and so on. And so the idea was that a vendor would be able to easily introduce support for P4 runtime in their target by implementing this this standard PIC API. And I think at some point, at least a few vendors did just that. And so the idea was that they would be able to reuse all the P4 runtime server logic, and which is pretty thin, and all the device manager logic, which is kind of like a decent amount of code. And just implement this API directly. And a part of the value here was that typically for those networking vendors, their drivers are already in C, and so they would easily be able to implement that C library. So from this API, we go to the BMV2 PI backend, which is just the implementation of the PI API specifically for BMV2. So in that case, we kind of like, we enter the realm of the BMV2 drivers. And while the PIC API is defined in this repo here, I think I'll just, no, I'll show an example later. Once we move to the BMV2 PI backend, this is going to live directly in the BMV2 repo. This is going to live in that folder here, BMV2 PI. All of those are files to implement the PIC API. And once we get to that backend, finally, we're going to interact directly with the BMV2 C++ classes, which kind of like, well, for example, there's a class for a match action table, and that class would implement the data pass behavior for a P4 match action table in the context of BMV2. And so basically the role of the BMV2 PI backend is to interact directly with that class and manage entries based on what the P4 runtime client is telling us to do. So from that picture, what exactly is simple switch gRPC? Well, as Andy pointed out, it's a single process, which is basically going to include all of those things. Of course, you have the simple switch library. So that part is kind of identical to the simple switch target, and it's built using what I call the BMV2 core libraries. So it's going to reuse that code because essentially simple switch gRPC is just simple switch with a P4 runtime server. So everything which is like a BMV2 object and data plane implementation is going to be exactly the same. But on top of that, we're going to add a P4 runtime server, the device manager, and the PIC library, those components we just saw on the previous slide. The PI BMV2 backend, specific to BMV2. We can also call that the PI BMV2 drivers, and then some glue code, and all of this is going to give you the simple switch gRPC binary. I've kind of talked about this in detail already, but let's. I think it's important to make a point of it. So the P4 runtime server is pretty simple. Its main responsibility is to implement leader arbitration and to invoke the correct method on the device manager instance based on the message received by the from the P4 runtime client. It's going to register callbacks basically with the lower level drivers to get notified when a packet in message comes in and needs to be forwarded to the controller. So this ties back to the stream channel, the RPC stream channel we saw previously. When BMV2 has, I mean, let's say simple switch gRPC, when simple switch gRPC has a packet in that it needs to send to the controller, it's going to basically call a callback function in PI, which is then going to be forwarded to the P4 runtime server, and that packet in message is going to be sent on the stream channel. As I said before, p4.org in PI, we have a reference implementation of a P4 runtime server. Stratum has its own server implementation, and when I say server here, I really mean that part that's in charge of doing leader arbitration. Because if you look at the Stratum code, what it does is for BMV2, all P4 runtime messages are processed by device manager. So if you look at Stratum and you look at this picture, only the gray box is going to be different in the case of BMV2. The rest is going to be the same code path. And something that came up in the P4 API working group recently is that it may be a good idea to unify the server implementation and have potentially a single library that can be used both by Stratum, both by p4.org to implement a P4 runtime server, and then we would avoid code discrepancies, and we would avoid a code duplication whenever there is a new version of P4 runtime, basically some implementations may be updated faster than others. So it seems reasonable that we could have like a unified implementation, in my opinion, as long as we don't introduce yet another level of APIs that needs to be standardized. I guess finally, another key part of the server, which is pretty much completely ignored by the reference implementation for P4 Lang, is that the server should also be in charge of authentication for the client. But basically, this is given to you for free by GRPC. So I think if someone wanted to implement this, it would be like very minor changes to the server code. And supports, for example, client certificates. Yeah. Device manager, we talked about this a lot. That's basically the glue layer between the P4 runtime server and the PIC API. I try to keep the device manager up to date as much as I can. Really, as we introduce new changes in P4 runtime, in the P4 runtime API, the device manager is really what needs to be changed. Typically, the PI API is pretty stable. So the logic in the device manager needs to be changed. And if by any chance the PI library needs to be changed, because I'll give an example. Right now, PI doesn't support stateful registers, which is why the reference P4 runtime implementation in P4.org doesn't support registers, and that's a complaint that comes up pretty often. If we need to add support for registers, the PIC API needs to be changed, and so you need to ensure that the version of the library consumed by device manager and the version of the library implemented by the BMV2 device drivers is the same, is compatible. So we do have and we use some dynamic linking here. So it's not something you can verify using a compile time check, but we do have a runtime check in PI init, which is a function that you need to call. I mean, that's called for you when you use P4 runtime, but that's used to initialize the PI drivers for your target. If there is a discrepancy in version number at that stage, it will give you an error, and it will segfault. So before we had that checked, it was really nasty to keep track of which version of PI and which version of BMV2 do I need, because essentially that's what it comes to. The drivers are hosted in BMV2. The PI library code is hosted in P4 Lang PI, so you need to make sure you use compatible versions. I wanted to talk about what happens when you do a set forwarding pipeline config in P4 runtime to push P4 runtime, to push a new P4 pipeline to a switch. So the RPC is going to be called with what we call the verifying commit actions.
Oh, Antonin, we lost audio there from you for a second. Do you hear us?
Time and the device manager. So we're going to call the corresponding C++ method in the device manager for that P4 runtime RPC. The parameters are going to be the same, nothing else changes. And then we're going to call directly PI update device start, which is the equivalent, once again, PI function for set forwarding pipeline config. This function has been there for a while. It predates P4 runtime. So this function is like the public API in PI. There is like a private version of the same function which starts with an underscore, and basically this is a function that backends need to implement in their drivers when they want to support PI. But there's once again a 1-1 correspondence, as this is done for historical reason. And this function, as I said before, is going to directly interact with BMV2 classes. In that case, BMV2 has a switch object and this object has a load new config method on it. So this function is going to be called, and it's how you tell BMV2, hey, here's your new BMV2 JSON. When I start giving you table entries from now on, they're going to apply to the new P4 data plane and not to the old P4 data plane. After that, in theory, there's some time where you can install entries for your new data path, which are not going to impact the current data path. So after PI update device start, the old P4 program is still being used, but if you send table entries, they're going to apply it to your new data path. So that gives you like a window of time in which you can prepare all your table entries, for example. But at the same time, packet forwarding using the old P4 program, the old P4 data path is not affected. In our case, because we used verify and commit, PI update device end is actually going to be called right after PI update device start. Once again, this is specific to the verify and commit mode of operations here. And what that function says is, okay, I'm done sending entries to you for the new P4 data path. I want to switch the data path that you're actually using to forward packets, and I want you to use the new one now. So what it's going to call is going to once again call a function from BMV2 called swap configs, which basically says, okay, I can swap the data path used for packet processing. So pretty straightforward in that case. It's really all like one-one mappings, and that's why everything in that chain is pretty much stateless until you get to BMV2. If you look at write, it's going to be like a similar story. The server is going to receive a write request. It's going to call the write method on the device manager. There are some functions called session init and batch begin, which were introduced to support some specific hardware network devices. In the case of BMV2, those are no-op functions. So batch begin lets you send multiple operations at once to the switch with the hope that it's going to be pushed to the hardware faster. But for BMV2, once again, those are no ops. We have a PI table entry add function, which is going to call the private version of the function, which is going to call a function on the BMV2 switch object. And once again, a write request can include multiple updates, for example, multiple table entry insertions or modifications. So we're going to repeat this step for every table entry which is included in the write request. Once we're done, we're going to close the batch. We're going to say that's all I wanted to send to you. If you're dealing with hardware targets that can support batches, at this point you're supposed to push all the modifications to the memories of your hardware. Then we clean up the session. If there, once again, in BMV2, this is a no-op. And if there is any error for any of the table operations, we can report that error to the client in a synchronous fashion. I'm going to skip packet IO. Yeah, a subtlety that I brushed on quickly before is that in PI, you have both public and private functions, and they're basically equivalent. The public functions constitute the public API. The private ones are the ones that need to be implemented by the backend. Most functions are just pass-through, but the idea for having separate functions is that potentially there would be some shared code logic, which is not target dependent, that you would want to implement in the PI underscore functions before you call the underscore PI functions, or some transformations or some sanity checks or things like this. And also, I think another historical reason was to kind of like support dynamic loading of drivers at that layer. So basically the PI underscore function would do a dynamic name resolution on the underscore PI functions. But in the case of BMV2, this is mostly relevant. And if you look at the code in PI, everything looks pretty much like this, where the only thing done by the public version of the function is called the private version of the function with no transformation whatsoever. I just explained all of this. Yeah, I can quickly touch on that as well. But basically, obviously, PI needs to have some information about the P4 program, information which is equivalent to the P4 info message. But because it cannot really consume it in protobuf format, because protobuf support in C is not great, we have like an equivalent C struct, which is called PI P4 info. And actually, the name P4 info comes from the name of this struct because this struct predates predates P4 runtime. But basically, we try to include all the information from P4 info with, if possible, no loss of information. I guess not very relevant once again, but it kind of is important if you need to add functionality to the BMV2 PI drivers, because this is the information that will be available to the backend, to the PI drivers for BMV2, not the P4 info message directly, but the PI P4 info struct. So you can see what it looks like in the case of a digest message between P4 info and PI P4 info. Some loss of information here, because you can see that in P4 info, we preserve all the information about the P4 type. So here you know that the message you're learning is a struct of type L2_digest_t with the following fields. In the case of the PI P4 info C struct, basically everything is going to be flattened, and that also corresponds to the packed representation of the message you're going to be learning in BMV2. Let's see how we're doing. Okay, we only have 15 minutes left, so I'm going to skip on that. But to make implementing the drivers easy, there is a very strict locking model in Device Manager, which kind of like guarantees that by the time you get to the drivers, to the backend, you don't have like concurrent calls for the same P4 objects, for example, the same P4 table, even if at the server level, you can have some concurrency when you process write messages. So the PI BMV2 backend, so this is what I was showing you earlier in the BMV2 repo. All those files here, here you go. We have, for example, _PI table entry add, and that's the implementation for BMV2, which ultimately is going to modify the BMV2 table objects with the appropriate entries. Skip over this. Let's see. Yeah, I'll do a quick demo because it's only going to take 5 minutes. Let me zoom in. Here we go. So here I have a folder with a very simple P4 program. I want to show you quickly how you compile this this program for BMV2, how you push it to a switch, BMV2 simple switch GRPC process, and how you can access it using the P4 runtime shell. So let me look at my cheat sheet here. It's just going to be a very simple demo. So I have a script called p4c lite.sh, which I maintain, which is kind of like a wrapper around the P4C compiler. What it does is it pulls a Docker image, which I also maintain, which as the latest version of the P4C compiler, including the BMV2 backend. This way I don't have to keep rebuilding the P4C compiler locally. I get the updates like on a daily basis, basically. So I'm going to compile that program. Once I get what it does is it pulls a later version of the Docker image, and then it's going to invoke P4C compiler on my P4 program. And all the outputs have been placed in that directory here. We can see we have the BMV2 JSON, and we have the P4 info message for my program. Once I have this, I'm going to switch to another terminal. Oh, oops, sorry, press the wrong thing. Here we go. And I'm just going to start the simple switch GRPC, which has been built by me yesterday and installed in that VM. And what I tell it is, I want you to start with logging to the console. You're going to start without a P4 program, so that argument is needed for historical reasons. And this is going to be your device ID 1. And so my simple switch process is going to start. I haven't attached any interface to it, so it cannot really process packets, but this is a demo about P4 runtime, so we're not going to process packets. Once I have done this, I can use the P4 runtime shell, which also is, let me show you, a project on P4 lang here, P4 runtime shell. And actually it's been quite active lately with several people contributing, so I'm quite happy about this. And it kind of like replaces the BMV2 CLI for those of you who are familiar with the BMV2 CLI. So once again, using that script, it's gonna run it as a Docker image, so I don't have to worry about dependencies and stuff. Or installing anything. This is the address it can use to connect to the P4 Runtime Server. You can see this is the port assigned for P4 Runtime by Yana. And here I'm providing the outputs from my compiler. So once I've done that, I can look at my simple switch GRPC process, and I can see some log messages. I guess ideally it should say that a new program was pushed. I guess you do have that message here that says that there's been a config swap and that your program is running a new data plane. You can see that the default entry was configured for some tables. Those are my tables that I've defined in P4 program, and they will be part of P4 info message. Those are tables which are auto-generated by the compiler to only apply actions. And yeah, now I'm in my P4 runtime shell. I don't use it very often, so I'm kind of like a noob. I'll put it in, I guess, okay, intuitive enough. I can type P4 info, and it's gonna give me the P4 info for my message, for my program, sorry. I think I can look at tables. So I have like 2 different tables. I can start building a table entry, for example, for the DMAC table. Here we go. And if if I do table entry question mark, it's going to display some information to me about how I can keep modifying that table entry and then push it to the device. So right now my table entry is empty. It just has a table ID. And a nice thing about P4 Runtime Shell, it does resolution between the ID and the name, so you know what you're dealing with. And well, I don't want to look into too many things, but let's see. Does that give me information? Okay, that gives me information about my table. So I can do, I think I can modify a match field like this for my table. Let's look at the match field we have. Dest address, and I can pass an arbitrary MAC address to it. Here we go. So now I have a match field in my table entry, and I think I can set the action like this. I really should have written this stuff ahead of time, but I think let's just use drop because it's simpler. Okay, here we go. So now I have a table entry with a match field, which is the MAC address I provided here. And I'm going to be able to add it to my DMAC table and say, every packet that matches this MAC address, I want you to drop it. And the syntax for it is just T insert, I think. Here we go. And if I look at my simple switch logs, it tells me that entry with handle 0, that's not a P4 runtime concept, that's a PI concept, but has been added to the DMAC table, and it's even going to print the entry for me. So after that, you can modify, add more table entries, read the table entries back, but you get the idea. And P4 runtime shell is still like being actively contributed to. So if you're going to use P4 runtime and BMV2, I recommend using that. In the time that we have left, let's talk about PSA Switch. So while simple switch GRPC can run programs written for V1 model, PSA Switch, as per the name, is going to run P4 programs written for the PSA architecture. It uses like a lot of the same C++ code as simple switch. So in BMV2, there is a concept of the BMV2 core library, which is everything under source BMCMIR, which has an implementation for tables, for example, and so on. So all of this is going to be common to all BMV2 targets, including V1 mol and including simple switch and PSA switch. Now, unlike for simple switch and V1 mol, where the externs are going to be implemented natively by the BMSIM library, by the core library, for PSA, you kind of have to implement those externs directly yourself in C++ as part of the PSA Switch code. And people who have contributed to PSA Switch previously, shout out to them, but they started writing some implementations for the PSA counter extern and the PSA meter extern. And those implementations are very simple. So basically the idea for PSA Switch is that ideally in the long term, it should replace both simple switch and simple switch GRPC for PSA programs. So in the context of PSA, I do not see the interest of having two different binaries. I think we should have like just one binary, which includes the P4 Runtime GRPC server. And well, here I kind of like give information about what happens specifically for PSA Switch when a table entry message is received by the P4 Runtime server. I don't think I need to get into details here because it's all handled by the BMV2 core library. So the implementation is exactly the same as for simple switch, and actually that functionality is already there in PSA Switch today. So there is no further work required to make this work. Actually, the demo I just did, I think I should have been able to do the same demo with PSA Switch because the same functionality should be there. Well, it's still missing the P4 Runtime server, but apart from that, everything is identical. However, as soon as you get into externs and, for example, meters, the implementation is going to be a bit different because for meters, simple switch, which is on the left here, is going to use a meter object, which is part of the BMV2 standard library, whereas in PSA, we're going to use an external implementation, which is going to be specific to the PSA target, to the PSA architecture, which is called PSA meter. Now, granted, this meter object is implemented by encapsulating an object of type BM meter. So we use encapsulation to avoid having to duplicate the code. And I guess I'll show an example really quickly. This is all the code for PSA meter. You can see that it's really a wrapper around the meter object. Actually, it's called meter array object from the BMV2 core library. But yes, but there are differences, and someone who wants to add new externs to PSA Switch and who wants to support P4 Runtime for those externs can refer to that slide and can refer to the meter implementation. I'll switch to that last slide here, where I wanted to talk about what are the items that need to be done if we want to have like P4 Runtime support in PSA Switch. And if someone is interested in contributing, they can refer to that list once again. If someone is using PSA Switch today, maybe they should also be aware of that list to be aware of the shortcomings of the current PSA Switch implementation. So if someone wants to contribute to PSA Switch and the P4 Runtime support for PSA Switch, I think most changes will be localized to the BMV2 repository. So you don't really need to become familiar with the PI repository and the device manager implementation itself. Of course, you need to be aware of what the code path looks like for P4 Runtime messages or the information that I just covered. But essentially, at the end of the day, what you're doing is you're only dealing with the PI backend implementation for BMV2 and the PSA Switch code itself, and that's about it. So the first task, because right now there isn't even a P4 Runtime GRPC server in PSA Switch, I think that's a pretty easy task, would be to add a P4 Runtime GRPC server to PSA Switch, and really maybe I should open GitHub issues for those tasks so that people can look into it and claim them if they want to work on it. But this should be pretty easy because you just really need to look at what's done for Simple Switch GRPC and do the same thing for PSA Switch. Once you have this, I think a few unit tests for PSA Switch that ensures that for the existing externs, P4 runtime programming can work. For example, meters, which I just worked, would be a good idea, I think. And once again, you can look at the examples for Simple Switch gRPC. There is the same thing, and you can just write like similar code using a PSA P4 program. Right now, we only have support for meters and counters as externs in BMV2 PSA Switch. So basically, we need all the other externs to be added to PSA Switch. And some of them are going to be difficult. Some of them are going to be easier. If you're looking for something that doesn't even have a runtime interface, like the random extern, or maybe there is an open pull request for this already, but that's a pretty easy one. A pretty difficult one is going to be registers. And I think an issue today in BMV2 with registers, even with Simple Switch, is the fact that we only support like fixed size registers with no type. So you can only store a 64-bit integer into a register, but people want to be able to store like structures, for example, struct types in the registers. I think this one, arbitrary data types, is going to be very complicated. So potentially started with a fixed size integer support is probably the right way to go, and then see where we can go from here. And finally, everything that's a direct resource, so direct counters and direct meters. Right now, we only have support for indirect meters and indirect counters. Is going to need some work with BMV2 core library. Basically, you cannot need a way from the match table implementation to notify those external objects so that they can quote unquote execute and either increment counters or update the bucket, the token state in the meter implementation. Same thing, digest. So I don't have a design in mind for all of those items. Some of them are pretty easy, so I kind of know what needs to be done. Some of them, like direct resources or arbitrary data type support for registers, or more complicated. That's one of those things that would be super easy if we were still using generated code, but we're not using generated code anymore. So so all that logic to be able to pack and unpack types when storing them into register is going to be like very difficult in my opinion. So I don't have a design in mind, but if there's a task you're interested in working on, you can let us know and let me know on the p4.org Slack, and I would be more than happy to spend some cycles helping with the design or providing feedback, code reviews, and so on. And I think if this is like a recurring meeting, I'm more than happy to pop on again and discuss a more specific item with the rest of the audience.